All right, who's ready to get started? Woo! Oh, happy Tuesday. Happy March. It's almost spring break. Isn't that cool? We get a spring break this year. Yeah, spring break. Shoot, I forgot. I'm just gonna apologize right off the bat because my stylus thing broke, so the tip's like a little janky. So my handwriting was bad enough. Now it's gonna be even worse. Yeah, and the dead spot over here. I'm just gonna stay away from that. Yeah. Okay. Well, few updates in it with everything. We do have lab this week. So today we're doing the Atterberg limits. I said it's a messy hands-on lab. It doesn't have to be a messy hands-on lab. It's definitely one of the messier ones because we're dealing with clay. But I did it actually last night and I wasn't covered in mess and clay, so it wasn't too bad. So just keep a hands-on or heads up for that. You know, we are working with like hands-on with soils for these tests. And this test is really important because it shows how sketchy geotechnical engineering is and how much room we need for improvement in research and all that fun stuff. So it's a really interesting one. And it's a really subjective test and it's fun. So homework 2 is also posted last week. It's due this Friday. So just don't forget about that. It's the soil classification. And then there's like one, subsurface investigation question on that. And I'm sure a lot of you guys already know because there's flyers every other foot in the hallway in building 4, but we have a construction and STEM career fair today. Even if you already have an internship and if you already like are pretty solid, not looking for a job, I definitely still recommend going just to meet other people and to get a bunch of free USB drives and stuff with logos on it. So it's worth going. UNF, like it's what they have here is like really rare compared to like other universities. Like the number of career or people from industry coming is like huge compared to like what I ever had as an undergrad and stuff at UCF. So definitely take advantage of that. All right, today we're talking about compaction. It should be kind of familiar to a lot of you guys if you took CE materials with me. We're talking about kind of like preparing the site before we build something on top of it. So we're covering in chapter 20 and then chapter 5 of these 2 textbooks. Last week, we were talking about subsurface investigation and the importance of that and the importance specifically of finding the parameters, like specific types of what I'm just going to call parameters of soil for the intended use. So if you're putting a structure on top of it, we obviously want to know the strength of the soil. If you're putting a structure on top of it, we also want to know the compressibility of the soil. So like how much is the soil going to change in volume whenever we put a load on it, like we put a house on it, we don't want it to just sink like 10 feet underground. And then also the other one that we talked about is the permeability. Permeability is the ease of water to flow through the pore space. In Florida, this is really big because most of the time we don't want water to flow all over the place because then erosion can happen, flooding can happen, that kind of thing. So the subsurface investigation is the test that we use to determine these like 3 things. And of course, we can determine a lot of other things along with it. But the question comes up then, like, what happens if we encounter soil that is less than ideal? So what if we're like, oh, shoot, this is really crappy stuff, but the landowner's like, sorry, I want to put my building here, make it work. Like, what kind of things can we do? The first thing that we can do is soil compaction. That's usually the go-to thing. Soil compaction increases that soil density. So we increase our unit weight. And it's mainly only performed in the shallow layers, but now we're starting to be able to perform it in deeper layers as well. So basically we can change the void ratio of the soil to fit whatever needs we have. So if we want it to be less permeable, we've already seen how the void ratio can correlate to the permeability. So if we decrease the void ratio, which means we're increasing the density, then we should expect a lower permeability. So we can kind of change the site conditions to whatever fits our specific needs. So we're all probably familiar with some type of compaction. Has anyone seen these things before? like on the road, driving in Florida, you see these all over the place. Now there's different levels of compaction energy that can be obtained through these techniques. And of course, you're going to choose whatever type of technique based off of the site conditions, but also the type of soil anticipated. So like these, obviously the one right here, like a plate compactor. This is for like small jobs, and if you're like putting in a pool deck or you know, just like doing small road work, this is pretty good for any type of soil. But the vibratory rollers, something like we've seen here, has everyone seen these before? Vibratory rollers. What about something like this? Has anyone seen this one? Sheep's foot rollers. So this one we don't really see often. We'll see that this type of roller is specifically used for clay soils. And in Florida, we do have some clay soils at the ground surface, but most of the time it's going to be like a sand or something like that. So sheep's foot rollers, you can see there is these like little, I don't know, I guess like the feet of it, or like these little like bumps in the drum. And that's meant to knead, like almost like you're kneading dough, because this clay, you don't want to just like smack it down. It actually needs to be like kneaded into compaction. So the vibratory rollers work good for like sand or some type of frictional soil, but then sheep's foot is used for clays. Then something, if we need a little bit more energy, we could have something like this. Has anyone seen these guys? Impact rollers. I've never actually seen one of these before, but you can see the thing in the back is what is compacting it. It is a like non-cylindrical drum. So as it rolls, it like will like fall over and actually compact it because of the unevenness of the drum. So that thing's just super heavy. And instead of using vibration, it just uses like the oblong nature of whatever. And then these right here, our buddy deep dynamic compaction. I think I may have talked about what this is in our CE materials class, but deep dynamic compaction is literally just a crane lifts a giant weight off the ground and then lets it free fall, and it compacts and hits the ground. And then they do this in like a certain grid pattern, and then basically you're able to compact the soil at a deeper layer because that energy is transferring all the way down. So all of these obviously have different amount of cost, but have different levels of effectiveness too. And they can also achieve different levels of compaction energy, which we'll talk more about here. But if just based strictly on soil type, each one is going to have its different level of effectiveness. So like the sheep's foot roller for a sec, for what we talked about last time, for clays, it's very good. So for clay soil, sheep's foot is going to be your like go-to thing if you have like a clay soil at the surface. And then you can probably picture like clay being one extreme end of this spectrum. For silt being somewhere in the middle, it's also pretty good. So I'll just say normally good. For domestic waste, just throwing like another like kind of, you know, random category here, domestic waste would be like landfills and a bunch of uneven like material and decomposing material. It's also really good. Actually, if you go to a landfill, I don't know if that's what you guys used to do growing up for fun like I did, but when you go to landfills, you'd see these things. These sheep's foot rollers are the ones out there. But if we're using this for sand or gravel, it's probably not your best bet. You're not going to get the most bang for your buck. You're going to be spending money on this equipment. You're not going to be fully able to utilize its compaction effort. So the vibrating cylindrical roller, almost the opposite of that. If we have gravel or sand, then this is going to be our go-to bet. So for sand, this is our very good option. I mean, that's why in Florida we see these like for roadways, because most of the roadway subbase that we're using is primarily like a sandy material, like an SM or an SW. And so that's why this is the most effective procedure for compacting. If we try to use this on silt, clay, or domestic waste, then we're going to have a hard time. So our impact roller and our deep dynamic compaction, anything that involves like impacting is usually going to have more energy involved than just the other two that are like vibratory or static. So for our impact roller, these are really good for gravel and sand. But for silt and clay, what we see is like this impact nature is actually like causing the clay to like form these little dips, because we know clay is like a plastic material, and you'll see that in our lab today. Like if you push on a clay, it's going to remain like deformed. So in this case, if you're using this on a clay soil at the surface, then instead of compacting it evenly, you'll literally just have dips of clay on the ground surface, and that's not going to be very good. Domestic waste though is kind of its own kind of animal, so these are generally good for that, because domestic waste can have all sorts of trash and just random things in it, so you need a little bit more energy to be able to compact it. And then our deep dynamic compaction, you can probably guess, very, very poor for our clay surface. I want them to actually like do this and see what it would look like, but just imagine dropping a massive weight on a clay soil. It'll just like, it'll be disgusting. The thing will probably get stuck, honestly, like in the clay, and you wouldn't be able to pull it out. So deep dynamic compaction is not used for clay. For silt, still kind of poor, but we do use this where we need a lot of energy. So for gravel, I'm just gonna put very good. And then for sand, it's pretty good too. And then for domestic waste, actually, this is our go-to thing for domestic waste. So a lot of times in Florida, actually, we'll use these deep dynamic compactions for not only domestic waste, but for mine tailings, like down in like Polk County and Bartow County, where all the phosphate mines are and stuff. Like all those mines from the 60s, they had these tailings, like the old mine scraps that they'd put in. And now that that area is building up so much off State Road 60, they're starting to do these deep dynamic compaction to improve the ground where these old mine tailings were, so they could put a bunch of expensive houses and stuff on it. So deep dynamic compaction is kind of interesting. I wanted to show this little video of it real quick that kind of illustrates the technique. And this is actually used by like at an old mine. Let me see if it actually will work. Okay, so what's one thing you observed from that video? What did you notice? Yeah, exactly. That's the whole process of this is, right? Like you take soil, when they are compacting it, what are they doing? Like, what are they actually doing to the soil? Like when they drop this massive thing on it and it creates this cavity, where's that cavity come from? Yeah, that's technically the void space now being rearranged and moving to the top, right? So if they move more mass of soil on top of it, mass of solid, then they're increasing that MS, which means we are increasing the overall density. Like from a logistics standpoint, like what else did you guys observe from that video? They spaced out the drops, yeah. So they do it in different different locations, and they don't do them right on top of each other. So that technique is actually like what we see is when you drop something, it radiates laterally away from that hole. So what's actually happening is like if you drop it at one point, the energy radiates, and then the other part it'll radiate, and the part that they actually need to strengthen is usually deeper. They aren't strengthening the surface layer. So yeah, they would drop it in that way. Anything else, like just like the location or anything? Yeah, the target layer, they want to be more efficient and actually compact that one specific layer. But when we start talking about stress from like the building load, like a person standing here, or like if I weighed like 10,000 pounds, like how would I be affecting the soil underneath me? Then you'll see like this will make much more sense, because like with depth, the soil is feeling less and less of me the deeper we go, and laterally the soil is feeling less and less of me the further away you go. So the same thing for a building, and we'll talk a lot about that like towards the end of the semester. Just logistically, you could see where were they? Yeah, pipeline, but it looked like they were like in the middle of nowhere, right? Like, so this type of technique is always going to be used in like an undeveloped area. Like you could not use this in, a downtown setting, because obviously that ground motion is going to affect the structures nearby. So like there's a lot of studies of just structural health monitoring. So during excavations, during compaction projects, even just like roadways being compacted with a vibratory roller, if you're doing that right next to a historic structure that's very fragile, then you have to ensure that the ground motion that you're causing, or the energy that you're inputting into the ground, isn't affecting the use of the structure nearby. So that's why anytime you see deep dynamic compaction, it's going to be in like BFE, like no middle of nowhere, because you can't do it next to existing structures and stuff. So you can check out like that Menard Group USA people. They have a lot of different things. But what is actually soil compaction? Like, what is it doing? So we've already said it increases the strength, and this is important for like slope stability. So the actual like, if we want this soil to be stronger, we don't want a slope to fail, like a scarp to form. It decreases the compressibility. So it's actually what we're actually doing is inducing settlement right off the bat. So we aren't letting that settlement, those changing of air voids, form over time. We're just making it occur right away. So then in the future, when we put our structure there, then we aren't going to have that settlement occur. This is really important for decreasing the permeability. So in mines or dams, like a lot of the earth dams that we have in Florida, there's this curtain of soil, so that is a very low permeability, so the water doesn't travel through the mine and cause piping or cause flooding on the other side. And it's also good to control the seasonal volume change. So we don't really have that issue here in Florida, but if you think about what happens when an ice cube forms from water, it expands, right? So like in areas that are less fortunate than us, that have frost and snow, if there's water in the soil in that pore space, and it freezes, then what's going to happen? It's going to expand, and we can have what's called frost heave. And this frost heave is really like problematic for like lightweight structures like houses or like apartments, wooden apartments or something. We can have uneven heaving, and then we can actually cause the structure to break. So this actually will control it, and we lower the pore space. So we lower the potential volume of this freezing action to occur. So overall, what this is actually physically doing, compaction is resulting in a decrease in air voids, which means it's increasing in density. That's all we're doing here. So if we are decreasing air voids, what type of soil, what state of soil can you think that we cannot compact any further? Like what specific case of soil? Remember, the air voids are what we're trying to remove. So what type of soil has no air voids? Yeah, 100% saturated, right? So in this case, if we have 100% saturated soil, what would happen if we tried to compact it? Yeah, nothing would happen. Like the volume wouldn't change, because if you remember from a long time ago, our Poisson's ratio of water is 0.5, which means the volume, if we compact it this direction, then it's just going to expand in the same direction this way, like a water balloon, right? Like a water balloon full, if you squeeze it this way, it's just going to expand the same direction. So if that water is in the pore space and we compact it this way, it's just not going to compact at all. It's just going to rearrange the particles and we aren't going to get a change in volume. So the main reason why we would do soil compaction is it's inexpensive compared to soil removal. Like if you think about it, and we have like a roadway going through a site, and the first 15 feet of soil is like not the greatest. Like technically, what we could do is, all right, let's just remove all that soil and then replace it with nicer soil that is stronger, has a better like density or something. But that's not always going to be feasible when you have a 500 long foot roadway. You know, if you have a single house structure, a single lot, that might be an option. But for some of these things, the price to remove the soil outweighs it, so we have to compact it or improve the soil that's actually at the site. So soil compaction, we've already kind of discussed like the process of it. But remember, this goes back to like the phase diagram. So all we're doing with compaction is applying mechanical energy. So we are applying like some type of force, some type of kinetic energy to it that is decreasing the air voids. So if we have this soil in these three phases before soil compaction, after compaction, we have less of an air void. So we aren't changing the solid yet, and we aren't changing the water, right? We're just changing this amount of air voids. So after more compaction, that's what happens. We just keep going. We keep removing these air voids as the actual soil particles like rearrange and they, you know, fall into a tighter package or tighter like fabric structure. And so then what we would do after that, like you saw in the video, is now we replace that change of volume with more solid material. Now, technically this solid, the soil that we're bringing over, is 3 parts in itself, right? Like it has that solid, as we move it over, it has water, it has air, whatever. But the fact is that we're adding more solid to the entire thing. So what this is actually doing is increasing that density, right? Because now we have more solid in that area. So even though this like makes sense to us, like physically, okay, like that makes sense. We increase the density. It really wasn't until like the 1930s that it was able to be quantified. And this dude, who has, I think, the coolest name, Dr. Proctor, in the 1930s, he was the one who first developed the quantitative way to measure the compaction of soil in the field. So before, it would just make sense. Farmers were like, oh yeah, if the cows go over, then the soil gets stronger and harder and stuff. But you know, like us nerdy engineers, we're like, let's put numbers to it. So this guy actually was the first to do that. And the interesting thing is the project that he worked on, the Bouquet Canyon Dam, I think it's in California, like Western California, Eastern California. You can still go there, and the dam is like, you know, still like its original state from when he helped construct it a long time ago and stuff. So what he actually did, like using his like engineering brain, he found that the extent of compaction, so how much energy that we apply to the soil and the resulting like density, is dependent on 4 things. And first, it's the dry unit weight. So the dry unit weight is like the gamma D, right? Or just the dry density too, so either one. It's also dependent on the compaction effort. And compaction effort is just another way of saying the energy applied. So back in farmer days, like how many cows are walking, how heavy are the cows, how many passes of the cows are going through, like how much energy is actually being applied. The other one that's probably obvious since it's a soils class is the soil type and the gradation. The gradation plays a big role into it. And then does anybody want to guess the last one? What's the other parameter that depends on the soil or that affects the compaction? Yeah, water content, right? Yeah, the water content or the moisture content, same thing. This plays a big role. If you remember from our lab in CE materials, we already saw this, and that's what we're going to be doing in this class again, determining the optimum moisture content. There's a specific point where there's too much water that the particles will actually repel each other because there's too much water. And if there's too less water, the water content's too low, then we have actually the particles not being lubricated and they're not wanting to roll on top of each other and fall into place. So the theory is first, the compaction effort is that measure of mechanical energy input into the soil. So in the lab, we can recreate this using what the guy, again, with the coolest name, Proctor, he named a hammer after him. So Proctor hammer. And we use that in the lab. But in the field, what this is actually representative is the specific type of equipment that we're using, as well as the number of layers that we're performing this test, and also the number of passes, right? If you have a hammer, just a regular hammer, and you just hit the ground once, then that's going to apply a certain amount of energy. And although we aren't changing the weight of the hammer, if you hit it a bunch of times, then the soil is going to be in a denser state. So the number of layers and the number of passes of our equipment is just as important as the weight or the amount of energy that it can apply once. That's why you saw the deep dynamic compaction occurring. They drop it in the same hole over and over again because they're increasing the density. So the water content is the other very important thing. And this is because the water content is dependent also on the gradation and the soil type as well. So as I said before, you think of it as a line of optimization. So if we have water content of 0 in our soil, then all of these particles, all these little grains are going to be stuck together. Especially if they're frictional, they're not going to want to roll on top of each other and to fall into the actual void space and compress. Now, on the other end of the spectrum, if we're close to the saturation moisture content, then there's going to be too much water. And as we apply energy, those soil particles are going to repel each other because the water is incompressible. And just like a water balloon, it's pushing everything away from each other. So there's a point of optimum, which looks like this if we were to plot it, a point of optimum moisture or a optimum water content that corresponds to the maximum potential density. So again, this is kind of our way of measuring compaction or quantifying compaction in terms of dry density. If we know the more we compact soil, the higher that density is. So this point of maximum density corresponds to this optimum moisture content. Now, most shapes or most soils are going to look something like this. It's called a sawtooth curve, right? It goes up, it goes down like a sawtooth. But the angle of that is going to be dependent on the type of soil, like the gradation of it or the actual mineral structure of it. So let's just say this is for a specific type of compaction energy. So this is just us taking a little handheld hammer and hitting it once. If we were to hit it twice and do 2 times the amount, what we would see is this curve would have the same shape since we're not changing the soil, but that curve is going to go up into the left. So it makes sense physically, right? We apply more hits, we're applying more energy, so we should have a higher density, right? So on our y-axis, we have a higher energy. But what we see with higher energy comes a lower optimum moisture content. So we need less water for those particles to be lubricated and fall over on top of each other so they can fall into place easier. So more energy equals a higher density, right? Makes sense. But it also means a lower optimum moisture content. So you may think, okay, this is better. Like we just always need the highest amount of energy at our site because then we can achieve the maximum amount of density. But what happens if you're in a project site where the natural moisture content is like super high, right? Because it rains all the time or you're near a swamp or something. So that in that case, like we might not be able to achieve an optimum moisture content that low because we can't like dry out the site because of just field conditions. So sometimes, you know, especially in Florida, you have to optimize the type of compaction equipment you're using so you can still reach that optimum moisture content physically in the site. So what we see, as I mentioned before, if it's the same type of soil, so the same gradation, we have the same curve shape. It just will shift up and to the left. So down here, remember, like what this is actually showing is like we are removing the air voids and we're replacing it with solids. And so that is increasing the dry density. So that means that theoretical, can't speak, that theoretical limit is our saturation curve. So once we reach saturation or zero air voids, then there's no voids, there's no air voids to remove. So our compaction can't go any further. So that's why for us here, you'll see what if you were to plot this, there would be this upper extreme where there's no, we can't have any data to the right of this curve. Because this saturation curve is when the density, when our soil is at 100% saturation. And when we're at that, we can't go beyond since we're not removing, or we can't have any air voids. So this is the theoretical maximum of our compaction. So there's another important line that we can see by connecting these optimum moisture contents. Again, if we're using the same soil type, what we'll see is this shape or this curve should look identical. We're just shifting it. So if we were to connect those maximums, then what we have is the line of optimum. So this is a specific like to a type of soil. So this is specific to soil like gradation. So like a silty clay will have a certain amount, like a gravel will have this. And this line of optimum is good because now we can just simply determine what type of energy we're applying and then find the corresponding water content and dry unit weight based off of the energy that's applied to the field. So like some of the examples look like this. Like what you'll see here is that these are all the sawtooth shape, right? Like these are what we call sawtooth curve. It looks like a saw or a shark tooth or whatever you want to think it of. But you can see that for like the clays, 4, 5, and 6 and the silts, generally trend to be less of a change in density with water. If you see like the shape is more wide. So for clays, like it's a more of a wide sawtooth, where for some of the sandy soils right here are more sharper sawtooths. So for the coarse grain, again, this is because the coarse grain is affected by gravity. So this is like physically we are applying forces and we're changing the structure of the, you know, the structure of the minerals, and we can actually like get it to compact more. But with our fine grain, it's all controlled or affected by the moisture. So the moisture plays a wider role. So you'll see that the x-axis here, we have larger, wide range of changes in the moisture content for fine grain soils. And again, what we see is those zero air void curves. They just cut the whole plot off, but you see there's no data here because that's beyond the physical limits. We can't compact it any further to the right of this curve. So the good thing about compaction is we have a very theoretically sound test in the lab that we can do to estimate and the optimum moisture content, and then we correlate that or extrapolate it to the field conditions. So the standard Proctor test was to develop the simulated field compaction in the lab. So again, this saves so much money because now we're doing a very easy test in the lab and we are normalizing it based off of the energy. And if we can determine the amount of energy that we're applying to the soil in the lab, then we can call up the contractor who owns all this fancy heavy equipment, all the rollers and everything. And we can say, hey, we need to equal this amount of energy. Then they can just tune in their machines correctly or use the correct amount of machines and apply the same amount of energy in the field as we were actually measuring it in the lab. So the purpose of this is to find the optimum moisture content at which the maximum dry density or unit weight is attained. Usually what we can find from this test is we can actually find the line of optimum. That's normally what's occurring or what we do. So then we just get a better understanding. If the contractor were to change the amount of energy, we could then determine where that would fit on the curve. Again, the important thing is this allows engineers to do trial and error in the lab and not in the field. So it's much easier to do trial and error to determine these tests on a small sample that you can control in the lab than having the contractor go with their equipment and go over and over again and do trial and error on a roadway where the project timeline is sensitive and you got to get it completed on time. So the lab compaction effort is found from, again, he named everything after himself, the Proctor mold. He's got a hammer, he's got a mold, he's got a test, everything's named after him. And then it can be compared to the field compaction effort, and that is from the actual machines. So this is like our sheep's foot, our rollers, our deep compactors, whatever, I don't know how to spell, it says dude, deep compactor, etc. So all of these big machines that we're using, we can calculate the energy from them. We can simulate that energy from our lab compactor, and we can make sure they match so we get a good understanding of what's actually happening. So the standard Proctor compaction test is the one performed normally. We also have a modified compactor test, modified Proctor hammer. But basically, it's not rocket science here. He just standardized a drop height, a weight, so then we could easily predict the amount of energy that's being applied to it. So we know that we can find the density since we have a set volume of a mold. So this is the mold. We know this volume is calibrated. So if we find the mass that's in that volume, then we get the density. And then we use this hammer to apply a certain amount of energy to that mold, and we change the density. So by knowing the dry density, we can find, the density, we then find the moisture content of the soil. By now, we all know how to find the moisture content, stick it in the oven, take it out, take the mass before, after. And then we can then correlate and find the dry density using this relationship. That's why that one's really important. So our moist density or our natural density, our density with water in it, if we divide that by 1 plus our moisture content, then we get our dry density. And then dry density is what is shown for our compaction energy. So what we would actually be doing and what we're going to be doing next week for the lab is the standard Proctor test. So we do multiple tests on the same soil and we're changing the moisture content. So as you see here, we're increasing the moisture content with each test. Each test we get a different gamma dry because we can measure the mass. And then what we should hopefully see is if we're in that right range of moisture contents, we'll see the density go up. And then as we add too much water, it'll start going down. So although we're just doing each one of these discrete tests, discrete points, we connect it with this fun little curve, and then we can estimate that optimum moisture by the peak of that curve. So again, like we would do this test here, and what we would see is if you change the number of blows of the hammer in the field, on the same soil, in the lab, then we would see the same shape, hopefully, but it would just be shifting up to the left. We could find that theoretical line of optimum, and that function is relating three things. It's relating the moisture content. It's relating the max density, right? Because that's the things on our graph. But then it's also relating a third thing. This is like in the z-axis, if you could picture it like, coming out of the paper. But this is also the energy applied. So although we're used to always seeing like these functions on a plot in terms of two variables, we can actually set up a function in terms of three variables and have like a 3D representation of if we have a set moisture content, a set dry density, then we can choose the compaction energy or any combination of those three. So the Proctor energy we can calculate by the following. So we know the weight of our hammer. We multiply it by the drop height of the hammer. And then we multiply that by the number of blows of the hammer, so the number of drops. And then we multiply that by the number of layers. And then what we divide that by is the volume of our mold. So the actual volume of that. So this is how we can actually calculate the energy of the standard Proctor hammer and how we can also control the energy. So if the contractor says we only have machines that can apply this amount of energy to our soil, or to your site, then you can change the number of blows, you can change the number of layers, or you could get a different hammer and change the weight. So you could simulate that in the lab and determine the optimum moisture content, and then tell the contractor like what moisture content the water needs to be at or something like that. So this is in the lab setting, and we can easily find the compaction effort or the compaction resulting because we know the volume of our soil, right? But if you think about it in the lab or in the field, how can we find the actual volume of our site? Like we know that we can like take a sample out, but as soon as we take a sample out of the earth, then we're changing the volume. So like, how do we actually check the dry unit weight of the site sample or the site? So there's three density methods that are used to determine at the site. One's called the nuclear gauge method. This one is literally like, I don't know exactly, but it's like a box that shoots out like some like nuclear things like gamma rays or something that like you have to get a special permit to do. But that measures the time it takes for these particles, these like subatomic or atomic particles to travel a certain distance through the soil. And then it correlates that to density. So it's a pretty crazy test. The other one is like a rubber balloon method. So think all the technical craziness of nuclear gauge and just think the complete opposite of that. Like they literally, you dig a hole and you put a rubber balloon in there and then you determine the volume of material that it takes to fill that balloon. So complete opposite of nuclear gauge. And then the most common, the one that we're going to be doing in lab 6 is the sand cone method. And basically what the sand cone method does, we'll do this in lab 6, but the whole issue with finding the density is determining the volume. Like if you were to go to the site and dig a hole and then take the mass of soil that you took from that hole, you could easily calculate or find the mass of that soil, right? By putting it on a scale. But how do you find the exact volume of the hole that you just dug? Like even if you're super good with a shovel and you dig a perfect, cylinder, it's not going to be a accurate representation of the exact volume of that hole. So the sand cone method, basically what we do is we have a sand that we know the set specific gravity of. So if we then determine how much sand it takes to fill that hole, and we know the specific gravity and we can calculate the density of that sand, then if we know how much mass it took to fill that hole, then we can back calculate and determine the volume of sand, and then we know the volume of sand, and then we know the volume of the hole. It's a lot easier when you actually see it hands-on than me trying to explain it at 8 a.m. So we use these two methods, or three methods. The nuclear gauge is one most common by contractors because they have the money and people are willing to pay for it. But sand cone method is still used a lot because it's cheaper, it's safer, and you can do it a little bit quicker than the nuclear gauge method. I mean, it's not requiring a bunch of safety equipment and stuff. But what we're trying to do again at the site is to achieve this maximum dry density at the project location. So if your contractor is super, super good and you say, I need a density of 110 pounds per cubic foot at this moisture content, they're like, I got it. And then they go and compact it. 99% of the time, they're not going to be able to achieve it on the dot, right? Because it's different conditions. It could rain, it could have higher humidity. The machines aren't 100% calibrated to reach that specific density. So although it'd be nice if we could get it exactly how we ordered it, it's unrealistic to achieve that maximum density or the optimum moisture content in the field. So we can't ever actually achieve it on the dot. So what we do is we usually have an accepted range of criteria, and this is based off of the project sensitivity. So typically what we see is it's anywhere between like 90 to like 99% of the max dry density, but it could be less. Like if you're just doing like a low volume county road, then the engineer might be like, all right, we're safe with like an 85% of the max dry unit weight. But if you're doing like a power plant or like something that is like, super high rise, then you want to get it as close, there's less room for error. So what we use is the relative compaction to quantify this. The relative compaction is a easy number. It's in percent and it's an actual percent. So all it is the gamma dry in the field, so the actual measured, and then we divide that by the gamma dry maximum. So the gamma dry max is the one found in the lab in our perfect conditions, without any variability of nature or climate or anything. And then our density in the field, this is from our nuke gauges or whatever these three things that we set up here, sand cone, one of these tests. So this is what the contractor would then call you and say, hey, I found a 97% relative compaction. Is this okay? And then you'll be like, all right, you're good to go. If they say like, if it's within that criteria, then usually it's acceptable. And that's all based off of this project sensitivity. So no projects are the same unless you're like doing like a FDOT road or something. They have their own specific criteria. So what that actually looks like for field compaction, again, if we have our optimum moisture content and our maximum dry unit weight from our fun little curve, and we have those two values set, and this is like the goal to get an optimum moisture content of this here. This would be our goal. But we can't always achieve that. So if we say like, instead, okay, the acceptable relative compaction is 95% for this project. So what that would mean is if we have our relative compaction of 95, that would mean our Field, acceptable for the field, is anything greater than 165 megagrams per cubic meter in this example, right? So what then you would do is read, okay, this is 95% of our maximum compaction. But you can also see there's two moisture contents that apply this. So we could achieve a lower moisture content and have this density, or we could achieve a higher moisture content and have this density. So there's this range of acceptable moisture content. So the range of moisture content in this case that would be acceptable that the contractor will try to reach is somewhere between 13 and 19% in this example. So the question is for this then, would we want to be on this side, like wet of the optimum, a higher moisture content, or a lower or dry of the optimum content? What side, what do you think is best to achieve? Dry of it? Yeah, right. I mean, it's kind of a trick question. It depends on so many things, mainly environmental conditions. If you know there's going to be a higher potential of raining, like in the summer or something, then you usually want to go less because most of the time it's going to rain and you're going to increase it. If you're in the dry months or something, or if you're in a drought and you know that you have a potential of losing moisture from the evaporation, then you want to go wet of the optimum because it might come back. Aside from climate, there's a bunch of different ideas and opinions on which side is better. And this is kind of like something that a general guideline that we show here. So the big thing for permeability, if we are trying to compact this material for a permeability project, like a project where we're controlling the permeability, then we want it to be on the drier side of the optimum. So this has it'll have a higher permeability if we're on the drier side of the optimum. If we're on the wet side of the optimum, then it'll have a lower permeability. So all of these random things you can see effects. And what you see if you try to color coordinate it and see which ones are the good ones, which ones are the bad ones, you'll see it's kind of split down the middle. So a lot of contractors that you'll work with, if they're working in an area, they will prefer to work on a certain side based off of their physical hands-on experience. And the best bet for you as an engineer is to trust your contractor in that case, because they don't like it when you argue with them on what it is, especially if it's not clear cut, if it's either wet or dry of the optimum. So for this whole thing, there's no set or preferred side of the optimum. And it's nice for you because you get a range of moisture content and you can use your judgment environmentally if you're in a drought, or if it's about to be rainy season and your project gets swamped with rain all the time, then you can decide that way. But most of the time it's going to depend on the contractor. Also machine problems, how old their equipment is, if they're not reliable, that kind of thing on that as well. So moral of the story for field compaction is trust contractor. Don't be that engineer who thinks they know this kind of stuff. This is the contractor side of thing, and yeah, we deal with all the fun numbers and stuff, and they deal with the actual construction of it. So any questions on field compaction? We'll get to see it hands-on in the lab at lab 6, like how we actually measure it. I think it's a really interesting test and a good example of the use of the specific gravity of the material. There's no questions, that's it. We'll start the lab still at 9:30 for everybody. If you're going to the career fair, see you guys over there. Whoever can get the most free stuff will win a certain prize. And I don't know, by capacity of thumb drives. So.